So the element which is the smallest is going to be this, right? Because independently defined element, like greater than this is greater than this is greater than this, right? So what's the smallest? The root, right? Induction, right? Okay. So now that is why. So now let's look at how insertion would take place, right? Okay. So now let's say we want to insert the data, say 4. Okay. So how do we do it? Look at the next element, the next position. As I told you, we have all the elements filled up except for the last ones. Okay, like we never have any missing elements, and we will not have some. So I'm just going to store it in an array. Like this is going to be my array index 1, a of 1. This is going to be a of 2, so on, right? Okay, so now I'm just going to store it such that a of 1 to a of n is my complete heap. Okay, anything after that or anything before that is not a part of the heap, right? Okay, so if I want to insert something, I'll start off by inserting it at the next free position. So what's the next free position? We can't have something out here because we can't have 3 children, right? Okay, so we're coming out here and we insert, say, what we put, okay, right? Okay, but now what do we notice? That 3, 4, this is fine. It doesn't cause any problems because we already have a smaller child, smaller value as the parent. So this is not a problem, right? Okay, so let's take another example where something would be, okay. Let's take, say, we want to insert another file. So there's already a file, but just for the, say, we want to insert another file. Okay, so this will also go out here. There's not a problem. So you just keep doing this. 6, 7, 5. Okay, so now out here, say you want to insert a 3. Okay, so now what we need to do then? This is going to be the first child. That's going to be 3. Okay, but this is not causing a problem now because we have a smaller element, which is the child of a bigger element, which is not proper according to our concept of a heap, right? Okay, so now the simple solution to this problem, or just keep on swapping these values, right? Okay, so at 3, so you see that, okay, that this is bigger. So what do we do? Just make this a 3. Just make this a 6. Now just see, is this proper? Not proper yet. Okay, because there's a 3 out here and there's a, okay, so how does it become like this? We had a 3, we had some value whatever, and we had the 6 went down, right? Okay. 16, okay, right? Okay, so now this is still a problem, right? So we just continue this procedure that we just swap with the parent, right?
Initially I think 6 was down, below 7.
16. That was 16.
That was 16, okay. Right? So I swapped it, as I put 3 out here, which I have swapped with the parent, right? Now continuing this procedure till there is no more conflicts, right? Okay, so now say we see that 3 and 7. Okay, this is again a mismatch. So what do? We just put a 3 out here, we put a 7 out here. Okay. Now you can just try to prove this yourself that this procedure of always swapping with the parent will always give us a proper queue, a proper heap once we are done. Okay, meaning that there will not be any more conflicts of this sort out here or anything else, right? Just try to prove that yourself. That say there are already some other children out here, so you just want to prove that when you do this procedure, the heap property gets maintained. Okay, like there's no this will never happen. That this is a 3 out here, there will be a 2 out here. This will never happen when you keep following this procedure. Why is that? Because if there was a 2 out here, that would mean that this 7, okay, have to be smaller than the 2, right? But then that would mean that the 3 would remain out here, it would not come out. Getting it? So that's a rough idea of a proof which just says that that the remaining structure of the heap doesn't get affected by just performing this operations, right? Okay, so now insertion into a heap has become pretty simple, right? You can just, I'll also show the implementation, I'll write down some code later on. Just come to a concept part right now. Okay, so this is your basic about your insertion. So talk about the complexity of this procedure, like the algorithmic complexity. So any idea about it? Simple, pretty simple. Right? Because why is that? Because if we have n elements, and as I told you that the property is that we always have that we have like storing them sequentially. So that means that if we have say 2 raised to n elements, the depth of this tree would be simply n plus 1. Getting it? Right? Because you can just consider, right? 1, 2, 3. You can just work out the details. You know the answer already, so I won't go into the details. Okay, fine. So this is your simple insertion. Now let's look at deletion. Okay, so just look at a simple concept that the deletion of we always extracting the minimum element, right? Okay, so now let's look at that you want to say extract this one and you want to remove the one from the heap. Okay, so now what do we do? As I look that after this operation, there will always be n minus 1 elements in the heap, right? Okay, so what we can do is that we want the elements to be from 1 to n minus 1. So that the nth element, that's a 16, we'll remove that. Okay, remove that in the sense of decrease the size of the heap, doesn't matter, this will always go out. Okay, and put the 16 out here. Okay, on your first, on the top. Okay, now again the same procedure that you have some So now it's a reverse procedure. We were swapping up the heap, right? Now we swap down the heap, right? Okay, so now 16 is going to be greater than 3. Okay, so now there's another problem that if you have 2 and 3, so should we swap 16 with 2 or with 3? The answer is the smaller element, right? Because if we have 3 coming out here, this will cause a conflict. So that is why we swap with the 2. So this becomes your 2, this becomes 16. Just keep on following this procedure and you will have 16 in the correct position. Okay, so always swap it with the smaller of the 2 children. Okay, and talking about, of course, in the case when you have the smallest element at the top, that is your minimum, as you call it, the minimum heap. Okay, min heap. Right? Okay, so this is your basic 2 operations about your insertion and deletion. Okay, now let's look at another thing that if you want to delete something from the middle of the heap. Okay, not necessarily from the top. Okay, so see, you want to remove this element. Okay, so now what do we do? Again the same thing, that this element, this is the last element in the heap. This will be erased and this will come out here. I'm assuming the 16 has got in the correct position. Okay, so let me put it. This becomes 3, this becomes 16, this becomes 16, this becomes 4. Okay, fine. So now I'm erasing the last element and putting the 7 out here because I wanted to delete this element, right? Okay, so now, but again this might be causing some conflicts. Okay, so yes, decide, is it causing conflicts upwards or is it causing conflicts downwards? If it's causing, okay, so if now the element above it is already smaller, so it's not going to affect the part of the heap above. So we are just going to perform a heapify down operation, as we call it. Okay, we're going to perform the swaps down the heap and get this element 7 in the right position, right? So that's the concept of deleting from the middle of a heap, right? Okay, so now that gives you a basis for your priority queue. Okay, because right now what we have in this time, we have insertion in log n time, we have simple deletion in log n time, right? And we have minimum finding, just finding the minimum, not removing it, just finding the minimum in O of 1 time, because that is always at the top, right? So that gives you an efficient structure for your priority queues, right? Okay, so why couldn't an array be used for this? Because finding a minimum will become O of n, right? That's one thing. So we might have a separate variable which stores the minimum. But what happens when that minimum gets deleted? It was a second minimum element, right? So it becomes again, it's not an efficient way of doing it using arrays. You can just try some things, I don't know, minimum, second minimum, third minimum, so on. But then there will be a problem that what happens when you remove the 3 elements. Okay, so that is why the structure of a heap, right? Okay, so this always takes care of itself by rearranging. Okay, so now the